Welcome everybody to another seminar, Lógicos in Quarantine. On behalf of the Brazilian Logic Society and of the Brazilian Computer Society in the name of the Logic Interest Group, I would like to welcome everybody and thank Professor Carlos Areces, who kindly accepted our invitation. Carlos, thank you very much.
Hi, Bruno, and hi, everybody. It's very nice to be part of this initiative. I'm going to switch on my video for just a moment to say hi to everybody. It's nice to be here, but then I'm going to switch it off because my connection is not very good. So I think that I prefer to use it all for my voice. And then here are the slides. So I assume that everybody is seeing my presentation, my slides, everything is working well. Then I start. Everything okay?
Yes.
Yes. Okay. Then, okay. So let me start. So I don't know how many of you knows me. I know some of you, not a lot of people. I don't know the names. So I present a little bit myself. I'm a modal logician. My main work is so I'm a logician. I come from computer science, and my main interest is modal logic. And then I know that many of you are actually fluent in modal logic from the people I have seen in previous videos. And then even some of you knows about a particular topic I will be talking today, which is hybrid logics. So this is the themes we're going to discuss, but I'm almost more sure that if you are here, if you are on a Thursday afternoon listening to these kind of talks, I'm almost sure that along your history you experience what I call beauty in mathematics, and I think that the more general theme I'm going to talk is a bit about that. I'm going to try to present a result that it is about beauty, a really beautiful result in modal logic and in hybrid logic in particular. The work is not mine. It's actually the work of Patrick, Blackburn, and Jerry, which is a particular way of doing a completeness proof when you have the hybrid operators in your language. As I'm saying, I'm not sure how many of you knows about modal logic. So I try to do a little bit of everything, trying to go slow in some part, introduce some definitions, and then sometimes I'm going faster. Okay, so please feel free to interrupt me anytime with questions. As Alejandro was saying in his talk, I very much prefer to be interrupted and ask questions during the talk than letting all discussion go to the end. Okay, so do please interrupt me with any question, comment that you want to do. So this talk is in particular about completeness proof for modal logics, including hybrid logics. And then the idea is to start reviewing what I call the classical proof of this kind, the classical approach, which is via canonical models. And I'm going to talk a little bit about the history about that proof, how completeness comes to be and from where they come. And in particular, it's interesting to see that the inspiration for the proof that we usually use for modal logic actually comes from Henkin's work on the proof on completeness for first order logic, at least for what I was able to research. And then I'm going to show a bit how once you go into this logic, this particular modal logic, which we call hybrid logics, then you can capture even more ideas from Henkin's work, and then this is the particularly beautiful result I think Patrick and Jerry and then Balder and then perhaps my contribution managed to get. As I was saying, so I don't know how many of you knows already about modal logic and how many of you don't know about modal logic. So my apologies are twofold. So for those who know, sorry if I go too much into details, and for those who don't know, sorry if I don't go into enough detail, okay? But as I was saying, you can always interrupt me for questions, or even to say, Carlos, hurry up, this we know. Okay, so let's start about, as I say, I'm not sure even if you know what the modal logic is. So let's start from that. One of the things which I think are very interesting about modal logic is that they're very simple. At least when you start, you just take propositional logic, and then classically you will add these two operators. If you have a classical base, so if you have just a classical propositional logic, you can even add only one of them because the other is definable, and they are just the universal and existential operators. We call them diamond and box. And diamond phi, classically, so historically at the very beginning, it's read as that phi is going to be possible, while box is read as phi is being necessary. This, as I'm saying, is just like the classical reading. We still call them the necessity operator, the possible operator. Nowadays, we just consider them as some kind of guarded quantification. This will become more clear in a moment. The idea is that this is a universal quantification, this is an existential quantification, and the interesting thing is that even though you are in a propositional setup, you still can do some kind of quantification, as I'm saying, a very controlled kind of quantification. But classically, you can just start syntactically by taking propositional logic. You add these operators, then you can write formulas like box phi implies 5 or box phi implies box 5. And this was actually what happened in the language. This operator goes all the way to the Greeks, to Aristotle, who already discussed possibility, necessity. But then the idea was that, okay, so now we can write something like this, box 5 implies 5. And you could ask yourself whether this formula is valid or not. Valid, well, we don't even have a semantics, but the idea would be, well, do we want to consider it a theorem, an axiom, no? And then here you could use the intuitions on your meaning. You say, well, if phi is necessary, then should it be true? If it is necessary, then it is necessary that it is necessary, and so on. Okay, and if you go to the classical literature in the field, you will find, so I'm talking pre-semantics now, you will find a lot of discussion about whether to accept one of these formulas as an axiom or not. No? But the interesting thing is that this is very simple. So the idea, you start with a propositional logic, you extend it a bit, and then you can start playing. The other thing that I think is attracted a lot of people to modal logic is that they are very flexible, no? Because possibility and necessity are only some of the possible meanings. You can also capture or try to capture obligation or temporals or beliefs and so on. And all of these can be thought of as modal operators, and classically they are considered like that, no? And again, I'm trying to do a kind of historical review very quickly of how the field evolved. No, so the main point is that once that people started with possibility, necessity, and then through all this, then things got a bit complicated because, of course, without the semantics, just arguing at the level of intuitive meaning. It was complex, no? And in particular, you didn't have a guide on even when to decide when two actions were independent or not, no? So whether they were one in the basis of some proof system, one was derivable or not. If you can derive it, then of course there is not independent. But if you can't, then how you prove that not such a proof exists, and so on, no? So that's the situation on the field at that time. And then we're talking about, this is really, as I was saying, history. We're talking about 1960. At that time, Kripke enters. Kripke and a lot of people, because now the semantics, we are so much used to talk about Kripke semantics, but actually all these people propose almost at the same time a similar semantics. So we're talking 1960. And the idea is that to use the notion of possible words in a very mathematical setup to try to give semantic for this. And what it is a possible word, what is a possible word semantics? Well, you just take, in a way, this is what, again, what the first Kripke proposal was, just a set of words, and V is a evaluation function that assigns meaning to the propositional letters over this word. But it's easier to think about this as just a set of propositional evaluations. So you have something like that. This would be a model. The whole thing is a model. This is one valuation. This is another valuation. In this valuation, P and Q is true. In this one, only P is true. The first semantic didn't even have an accessibility relation. So just a set of propositional valuations. And then you can think that in this particular model, P is necessary because both words were P words. Then P was necessary because P was present in all the possible words that we wanted to consider. That's the original semantic of Kripke. And then in this particular semantic, it turns out that these two formulas are indeed valid. No, box phi implies 5, and box phi implies box phi, both are valid. Because here we don't have an accessibility relation. But now with this semantic, we have new tools to decide when a particular action is independent from another one, or when we want it to be valid or not. No? So that was 1960. Then a few years after, I don't think even, perhaps it was even the same year, or very, very soon later, Kripke also came with the idea of adding the accessibility relation that connect the words. And then now our models are just, now in a model way, we think of it as just a graph, a directed graph. And it just happened that it has a valuation, a propositional valuation in each point. So a label, what we call a label. And you can also think of it as just a relational model for first order logic, just that you don't have constant, you don't have functions, and your relational symbols are just unary and binary. No? And then in this setup, we get the modern semantics that says that box means in all possible words, but just possible means successor. No? So a point will satisfy box phi if all successors satisfy phi. And here I have, as you see, now we are more familiar. It's a graph. Now it's a directed graph. We have just valuations, a propositional valuation in each point, and then in each particular model at this point, we can falsify both formulas that we were showing before, because box P is true here, because all successors are P, but W itself is not a P word, and box P implies box P is also false, because the necessary P, all successors are P, but all two arrow successors are not P, okay? So, now this particular semantic gives us more models. Because we have more models, we have more counterexamples. So some things that before were valid, now they are not valid anymore. And then very quickly we arrive to some of the early contributions of Kripke, the first completeness theorems on this relational now semantics. Thus, Kripke realized that some actions were related to properties of the accessibility relations, like box P implies P is related to the reflexivity of the relations. Box P implies box P is transitivity. And then he managed to prove the first completeness results, saying, well, if you take some actions and then a class where the relation is reflexive, for example, then the notions of theoremhood and validity coincide. No, and now we are in the early 60s. Okay, with these papers of Kripke. Now, if you read Kripke's original paper, the proof that you will find there is not the proof that you will find at all in, for example, the Modal Logic book of Blackburn, derive, so the modern completeness proofs. Okay, Kripke proof was based more on tableaux method. So actually, it was Beth tableaux method who he used, and the proof goes a bit like this. So you try to do a tableau proof. A tableau proof is looking for a model, no? And then the idea is that when you fail to find a counter model for the negation of a formula, from that you can try to actually build a concrete proof of the formula. Okay. So this is the scheme of the proof in Kripke's original papers. And the proofs are a bit, especially if you read it today, a bit difficult to read. And also, as here it comes, Kaplan's, some years later, now 66 already, writes a review of Kripke's paper, and he criticized the proof, saying that they're a bit too sketchy. They use too much the intuitive structure of the tableau. Think that the tableau is a tree, it has structure, so it's a bit difficult to argue over there. And he said, well, I'm not sure that these proofs are the best we can do. And by that time, we have already the work of Henkin doing completeness, a model theoretic argument for completeness for first order logic. And then Kaplan proposed how to adapt Henkin's model theoretic proof for modal logics. No, so Henkin did it for first order logic, and Kaplan says we can use these ideas for the modal case, and this is how the modern proof of completeness appear. At least I think that I can more or less track it till there. Actually, this is the most famous reference, Kaplan in 66, where this first idea of completeness appears clearly. At the same time, you have the work also of Makinson and Cresswell, almost at the same time. Well, these are publication times, not clear when actually where the proofs were done, that propose basically the same idea again. And there is one paper which is a bit quite earlier, actually, Bayart, 1959, which is not usually so well cited because it is written in French. So it was a publication in French, so nobody read it till much later. Okay, so usually Kaplan is cited as the one that came with the idea of this particular completeness proof that we will review today. So let me now move really into completeness. Henkin completeness, now I'm talking Henkin's first order logic, proof of completeness for first order logic. If you go to Henkin's work, you find at least these two ideas which are crucial. One is the idea of using a maximal consistent set of formulas as your objects. Okay, so it's a construction that turns this notion of consistency, which is proof theoretic, and then you build maximal consistent sets, and then this object you put it in your model directly. No, so you turn syntax directly into semantics. No, and it's a great idea. And then the second point, because he's dealing with first order logic, is that you can actually witness quantifiers. So the quantifier, an existential quantifier, is claiming the existence of something. And then that you can actually put a constant as a witness for that existence. You say, well, if something exists, then let's use this constant to denote that thing. No? So you use that idea in the construction of the completeness in the completeness proof. And then going back now to modal logic, well, Kaplan and then also Cresswell and Makinson takes this idea, but of course the idea is that one, the use of maximal consistent sets directly maps to the propositional setting, no? Because of course you can also do maximal consistent set construction at the propositional level. But point two, the idea of using witnessing doesn't, because you don't have constant in a propositional set. In a propositional modal logic, you don't you are in a propositional setting, you don't have constants. Okay, so the idea is that they will took point one and propose a construction that uses basically just point one, and point two, this says, well, nothing to do about that. One thing that I didn't mention is I'm talking about modal logic, but really I'm talking about propositional modal logic and actually normal modal logic and actually classical normal modal logic. So I'm not discussing intuitionistics or first order modal logics. No, that's a different story. I'm talking about normal propositional modal logics. So was I saying 1.1 was easy to adapt, 0.2 not, okay? And a bit, the story that I'm going to tell today is that once you move into the setup of hybrid logic that I'm going to also introduce, then actually you can actually also take two into the mixture, so take advantage of two, and actually that leads to very interesting completeness results that are strong, okay, that are generic, and this is what I'm trying to do. Any question up to that now? Because now I'm going to start more technically working on the completeness proof. So if there is any question, I'm happy to take 2 minutes to answer. No questions.
Carlos, I have a question, Petruccio.
Yes.
Number, even if you get the modal logic formulas with the completeness of containers, it be some kind of useful in some completeness proofs or not? I mean, 2 is completely excluded, or maybe you can use it in some form, or you are using it in some form when you make the...
No, exactly. What I'm going to show is that actually, well, if you want to use the idea of witness, you need to have something to use as witness. And the main point is that once you introduce nominals, which is what one of the tools that hybrid logic gives you, then you definitely can use them as witness, and then you do a different kind of completeness proof for modal logic, which I think which is very, I'm not sure. I mean, it is the same complexity, the same difficulty of the previous proof, but it will give you a stronger result that I'm trying to show today. Okay, so that's the point. I think that the idea is that in classical modal logic, you didn't have the tools to actually take advantage of the idea of Henkin's idea that I show in point 2. Okay, but once you have a nominals and add then and satisfaction operators, then we will take point 2 and then run with it into a much general completeness proof. Okay, this is what I want to show exactly.
Okay.
Okay. Then again, well, and as I'm saying, I'm sorry if probably for some I'm going too slow, for some I'm going too fast. I hope that still the ideas are getting into place. Now I'm going to try to outline the standard completeness proof for modal logic, the one that used only point 1, and show a bit how it works. Okay, I'm going to try actually go through the proof in a bit of detail. Because then I want to show how once you have hybrid logic, and then I have to introduce hybrid logic, how you actually can take advantage of 2. You do some things a bit different, but then you get a stronger result. Okay, So let's try to do that. Now, to make things a bit more concrete, first, perhaps many of you doesn't know what the normal modal logic is. Well, this is very fast still, but we can think of it as just a set of formulas and think that you have all propositional logic inside, so all theorems of propositional logic. You have, of course, closed under modal ponens and uniform substitution. Look, that uniform substitution is important now because you also have a box and diamond. So you want to be able to say that, for example, diamond P or not diamond P is a theorem, so that tercero excluido, so excluded middle, holds for modal formulas. And then the only modal machinery that you put is the necessitation rule, that says if a formula is in the set, then the necessitation of that formula is in the set. And this is very clear that it is sound. If a formula is a theorem, then the necessitation is a universal claim on that. Says, well, if something holds, then it holds everywhere. It will hold in all my successors. That's why box 5 will also hold, okay, universally. So if 5 is a theorem, box 5 clearly is a theorem. And then the K action is the only additional action besides the one from propositional logic that you need to include, which is distribution of the box with implication, and it's a kind of modus ponens. It says, well, instead of having box P implies box Q and then box P, it says, well, if you have box of the implication and then box of the antecedent, then you get box of the consequent. And again, it's very easy to check that this is sound in the semantics I showed before in Kripke models. Is going to be sound. And that gives you, and then the set, no, so, and we call K, the logic K, the smallest modal logic, normal modal logic by this definition. So you have this, what is generated by this, and no more, okay? And then the theorems are the elements in delta. Okay, so, and delta is, but look at K is the smallest modal logic, but of course you can add some additional actions like the action for reflexivity, the action for transitivity. So the box P implies box P, and this will make your set delta grow into a larger logic. You can even throw inside bottom, and then it will be the set of all formulas, the inconsistent logic, but the inconsistent logic is going to be a normal modal logic. Not very interesting, but it's there. And the smallest modal logic is K. And then the notion of theorem, we know, it's just membership in K. But I'm going to be more interested in something even stronger than theoremhood, because I'm going to try to you can do a proof of completeness, but not for just theorems, but what is called strong completeness for the consequence relation. You can characterize semantically the consequence relation, so the relation of implication from a set into a particular formula. So that phi is a consequence in your system of gamma, of another set gamma of formulas, okay? So the definition of that, you can define it in this way. So syntactically is, well, it follows, it is a consequence of, it can be deduced from in the system if the implication holds for, look at gamma, it might be an infinite set. So you ask for a finite subset of gamma to be the antecedent, and then if you can prove the implication, then you say that actually is a consequence. Okay, so you transform this consequence into a theorem. Okay, and then in parallel you have the semantic notion, and you want to somehow synchronize these two notions, say that they are the same. You can capture now the. Sorry, what I'm saying, I didn't say that. Look, that this is more general than theoremhood, because theoremhood is a particular case where delta is the empty set. No, if delta is the empty set, then what you get is just theorem, because this conjunction trivialized. So this is the case where you can actually use other formulas in the proof of phi. And then there is a notion about global consequence, local consequence, but for the moment, let's leave it at this point, okay? What I'm saying is that you can do it syntactically or you can do it semantically. If this semantic definition is, at least for the people who think more theoretically, like myself, is the natural one. You say, well, when does a formula phi follows from another bunch of formulas gamma? Well, if in every model that I have in my class, whenever a point satisfies gamma, then that same point satisfies phi. I didn't mention it before enough, perhaps, but formulas in modal logic are evaluated at a particular point in my model. Now, remember that my models are graphs, so it will depend on where I stand in my graph to evaluate the formula. No, a point might be a p point, and another point might not be a p point. So for consequence, this is what's called local consequence, and it's the one that we're going to match here. If the point satisfies all gamma, so all the formulas in gamma, then it also has to satisfy phi. If that's the case in all the models in my class, then I say that it is a semantic consequence of my set of formulas. Okay. Okay, and then completeness means that I want if a strong completeness result is the one that says that the syntactic consequence coincides with the semantic consistency. Okay, actually, in one direction is soundness, in the other direction is completeness, but soundness we always take for granted. So we actually always, of course have to prove it, but we always say, well, if a logic is not sound, then it's not very interesting. It's a semantic, it's not sound for a logic, then we are in serious trouble. So at least we want the soundness part, and then in addition we want to be able to prove completeness. As I'm saying, since soundness is always easy to prove, because this notion, the notion of syntactic consequence, is somehow operative, so it can be generated by the axioms and the rules and so on. You just check that you never lose soundness, okay? That everything, the actions are valid and the rules preserve validity, and then this part of the proof is always trivial, very easy. The problem is the other direction, no? The other direction is the completeness part, where you have to prove that your system is strong enough to capture everything that your semantics says that it should be so. Okay, so here you have a general definition of what it should follow, and then here you have this operative definition of what you can prove, and you have to prove that, you have to now argue that you can prove everything that you need to prove. Okay, so this direction is the difficult one, and usually you to prove it, you flip it around, you use contrapositive. So you say, well, if I cannot prove, then it should not be the case, and then you juggle a bit with the definitions, and you end up that with what you need to prove is what's written here, this last line, that says that every set that it is consistent for your logic, consistent meaning that it doesn't derive the bottom, no? So if you cannot derive bottom in terms of this set, then actually you can find a model for that set. So now this is the way that you do modern completeness proof in model theory, where you say, well, actually it's a model construction, okay? And if you're a model theorist, then you are very happy, because the idea is that we have different ways to build models, okay? And this is the idea where we say, well, now we are using maximal consistent set from Henkin idea to build my model. And look that this is perfectly set up, because in addition, you know that your initial set is already consistent, and then starting with this material, you have to now exhibit a model. So this is the classical completeness theorem. The idea is that you build this model, and this is even very interesting, because look that for every consistent set, you have to build one model. You might even try to build one model, one different model for each consistent set, but actually you can do much better. You can build one unique model, which we call the canonical model, MC, M canonical, which actually satisfies all consistent formulas and actually all consistent sets of formulas. Here I should have said all consistent set of formulas, okay? So you just exhibit one single model, and that model works as the model that satisfies all your consistent formulas, and that's how you prove completeness. Let's advance a little bit more on that. So first, a maximal consistent set, then it's a set, as I said, consistency means that I cannot derive bottom in the system, in the axiomatics, and maximal consistency is that it cannot be extended anymore without losing consistency. So MCS, maximal consistent set, and this is again this comes from Henkin, the idea of you pick maximal consistent sets as your bricks for your model. So the first thing that you have to do is you have to show that you have enough of these bricks, okay? So that you can always start by getting the proper bricks, no? And this is called Lindenbaum's theorem also, because Lindenbaum was the first of doing this kind of construction. The idea is that you already are given a consistent set. You only need to make it maximal, okay? So you have to blow it up, but that's very easy. You can do it by enumeration, no? So you start with a set that you know is consistent, and then for every formula in this enumeration, if adding it preserves consistency, then you add it. If not, you will be able to add the negation, and that works because we are classical. And then if adding one it doesn't work, then adding the negation will work. And then you just take the union of all this chain, and you can argue that that set is maximal. So getting a maximal set without losing consistency is easy. It's done in this way. And then you're almost there, because your canonical model will be the set of all your maximal sets, maximal consistent set, and then you only have to say what is the relation and what it is the evaluation, no? Because you have to build the graph. So the points you already have, then you have to, and look at this is interesting because the points are now has a lot of structure. They are set of formulas, no? And you will use that structure to define the relation and the evaluation, because the relation is defined in this way. You have the 2 points that are maximal consistent set. When do you put an arrow between them? Well, you put it every time that you can put it. The idea is that if a formula, you put the arrow if and only if whenever 5 is in the head of where you want to put the arrow, then diamond 5 is in the tail of the arrow. The idea is that, well, if the 2 words contain formulas that agree properly, so that if this says 5, then the other say, okay, I accept that 5, I'm already saying that 5 is possible, and you say it, and they say it for all the formulas, then you put the arrow exactly in those cases, okay? So you put as many arrows as you can in the model, while you don't violate this idea that the sets have opinions, no? Some of them already have diamond formulas, so you have to respect those diamond formulas when you put your arrows. And then that's the relation. And then the evaluation. The evaluation is also very natural, but you have to know where you are going. The idea is that when is going to be true at the point, well, when it is already there in the set. So if it is in the set, then I make it true. Okay, because I have to say which propositional symbols are true. Well, the ones that are in my set will be the ones that are true, and only those. So you see that actually, usually the points are not very interesting in a model. All the work is done by the relation and the evaluation. In an arbitrary model, I don't care what the points are, but here in the canonical model, it goes the other way. Now, once I define WC, WC mandates what RC and VC are going to be, because they have all the information about how the model has to be constructed, okay? So now, one thing, if you think a bit about this model, you can notice one particular thing. First, it is a big model. Actually, it is uncountable, okay? Because, so the set WC is not countable. So it's infinite and countable because if you take a set of propositional symbols, an infinite set of propositional symbols, as we are assuming that we have, every subset of that set, every part of that is consistent, okay? And then it can be blown to a different maximal consistent set. So part of propositional symbols is the seed of my WC. So the set is big, is uncountable. Okay? And then the interesting thing is that already here, as we were saying in the evaluation, we are doing this work that said that whatever is in the set should be true in the set. And we do it for propositional symbols in the evaluation. That is the way, the door to prove the last thing that we need to prove, that everything that is actually in the set is going to be satisfied. So actually, better than truth, I should have put here satisfaction. So membership is the same as satisfaction, or at least being true in the point, because you can prove this result that says that, remember that the points are sets, so being in the set is the same as being true at that point in the model. And that's it. That's the whole thing that you need, because your model contains all consistent sets, okay? And you wanted to have a model that satisfies all consistent set, then because everything that it is in the set is actually made true, you have completeness, okay? Usually the only difficult case is the diamonds, and for that you prove the existence lemma. I'm going to skip that, but the important thing is that once with this construction, you get completeness, and it works very well. It works for all normal modal logic. So that means that for every delta that it is normal, that it is a normal modal logic, you get completeness with respect to its canonical model. So that's always works. The construction is fail-proof, okay? But also, it's not necessarily always what you want. And this is the last thing I want to show. And I hope that this is the point that it is important. Because for the class of all models, it's not a problem. It was easy. Remember that K was the minimal modal logic. So the minimal modal logic, you will prove that it is complete with respect to the class of all models. That means that your canonical model for sure falls into your class of models. So your canonical model is a good one. It's one of the ones that you were considering because you were considering the set of all models. So you have completeness with respect to your canonical model, and you know that your canonical model is going to be in the class you were considering. Nothing more to do. So the case for the proof for K is easy. If you go into other logics, so into bigger deltas, into bigger normal modal logics, not the minimal system, then you might have troubles. And actually, there are troubles because you for sure have completeness with respect to your canonical model, but it might be the case that your canonical model is not in your intended class. So it's not in the class. For example, if we add the action for transitivity, you want your canonical model to be transitive, okay? And that actually works. For transitivity, it works. But there are cases where it doesn't work, okay? For example, if you add that action to K, it doesn't matter what it is, your canonical model doesn't fall in the intended class, okay? This is So, and those are the cases where completeness gets complicated, okay? Otherwise, the method works very well. But the problem is that by applying the method, you not always ensure that your canonical model, it will do what it does, what it needs to be done, so it satisfies your consistent formulas, but it might not be one of the models that you liked to have, because you insisted in your models to be pink or green or whatever. And it might happen that when you build your canonical model, it doesn't have the properties that you wanted it to have, okay? And that's why, in general, it's difficult to give a general completeness result. You have to prove for each system, for each logic, you have to prove the completeness, because you say, well, I build the canonical model, and in addition, my canonical model is in my class. And that's the part that and sometimes you have to work to put it in your class. There are some generic completeness result that works very nice, like something that's called the Sahlqvist completeness or Sahlqvist formulas, that says for all formulas that are Sahlqvist, the model will always be nice. But these kind of results are difficult. The proofs are involved, and it always has to do with some second-order trick playing around there. Okay. So this is the state of the art in standard completeness proofs for modal logic. And now I want to talk about, and here the second point of Henkin, the idea of using witnesses, doesn't play any role, okay? And now I'm going to start talking about the second point, and for that I have to start talking about hybrid logic, okay? But again, this is a good point to stop for 1 minute and say, well, if more or less this was somehow clear, I can continue. If you have any question up to now, I can clarify something. So I switch on my camera also so that you can watch me, okay? Any question?
No question
okay.
for now.
Then I continue. So up to here, then this is very classical, and this is definitely what you will find in most textbooks, a bit advanced in modal logic, when they go into completeness. This is the proof that almost surely you will find if they do it more theoretically. These are the ideas. So this is very, very classical, okay? But as I'm saying, because look that there is nothing about witnessing quantifiers going on here, and you can say, well, of course not, because it was a propositional logic, okay? So nothing to witness, or at least nothing with what to witness, because on the other hand, we know that the diamond and boxes are quantifiers. So you can say, well, there were quantifiers going around, so why we didn't need to witness them? Well, we were lucky in a way, because if we had to witness them, we didn't have with what to witness them, okay? So luckily, we didn't need to witness anything. Now I'm going to show that once you go hybrid logic and you add that, and you will be able to witness your quantifiers, and then you say, well, but I didn't need to before, so why do we want to do it? Well, I'm going to show that if you do this additional work, you actually get a stronger result. Okay, this is the point of the second part of the talk. Oh, sorry, here. So hybrid logics, okay? Some of you know me for my work in hybrid logic. As I'm saying, the ideas goes back also very far away to Pryor's work, so same time of Kripke. But the main work on the field was done by Patrick and Seligman. The reference there are just too many to cite them all. They have a lot of work done also with Balder, Tenkate in particular. So what I'm going to say that there is this chapter in the Handbook of Modal Logic that we wrote with Balder, And don't read the chapter, but go to the references and look there for all the references to the work of Patrick and Jerry and Seligman, and look those, because it's also always a pleasure to read what they write. So so this is just a link to all the reference to the work of Patrick and Martin and Jerry's. What are hybrid logics? Well, one way to think about them is that you want to, there's a way of adding somehow constants and equality to the modal language, okay? And this, for many classical modal logicians, I remember when we were presenting these ideas to Johan, he was very skeptical, Johan van Bente, I'm talking. He was very skeptical because he said, well, there is no place for these things in a propositional language. And then with the time and with the insistence of Patrick and so on, he became friendlier to the idea. But the idea is, well, it's a propositional language. So how the hell you can say equality? What is equality of what? And how would you add constants if you don't have a term language? The idea is that all your formulas are propositions. So you cannot add constants which are just terms, okay? So this doesn't seem to really work. Well, and perhaps the first genius idea of Patrick and Jerry was actually to find a way to build this idea of having constants inside the language. So let's see how it's done. First, the idea is that, well, we will not add actually constants. We will add something which is a bit different, which are nominals. And nominals, we can think of them as just propositional symbols, okay? So in addition, initially they are just propositional symbols. They're just a new set of propositional symbols. And then, in addition, we will add for each of these propositions this modal operator, which we call at or satisfaction operator. So for each nominal, there is a diamond, a modality. They are self-duals, or they are at the same time diamond and boxes. But for each nominal, we have this satisfaction operator. Okay, so these are propositional symbols, but why can we also think of them as constants? The idea is that I'm going to insist in the semantics that each of these propositional symbols, they are interpreted as a singleton in my graph, okay? So their extension, their meaning, is just one point in my model, okay? Then, because the extension is just one point, it's true that it is just a singleton with a point, and because it is a set, we can think of them as propositional symbols, but it is a singleton, so it contains only one element. So somehow at the same time, they work as denoting just that single element, okay? So they also work as constants, okay? So nominals at the same time play the role of constants and propositional symbols, okay? The idea a bit is saying you can think that every name, every proper name, like Carlos Eduardo Areces or my name, you can say, well, it is a constant, okay? But if you think of it as the property of being Carlos Eduardo Areces, so just the property of being that thing, then it is a property. It's a proposition. You can take it then as a propositional symbol whose extension is the singleton me, okay? And the idea is that, so nominals are represented as singletons, and then the satisfaction operator, and that's also going to be very important, is evaluating the formula, but that way we call it at I phi, because it switch evaluation to the point I. Remember that I is a nominal, so I denotes a point. So it says, I'm checking whether in the point W, it is true that in the point I, phi is the case. Okay, so it lets one point say that something happens in somewhere else. Okay, so look, for example, that here in this point W, here nothing is happening, so it's completely empty. But at this point, it's also, he can claim that at I, P is the case, because in this point, which is the I always going to use I, J, K as nominal. So if you see them around, I, J, K are nominals, P, Q, R are normal propositional symbols. So at the I point, P is the case. And even W can say that at the J point, J is saying that at the I point, P is the case, as I'm saying here. Okay, so the at operator lets you talk about what's going on in other part of the model without moving there. The idea the diamond and box let me first move there, reach there, and then say what's going on there, but at directly move evaluation to the point where this is happening, okay? So, okay, why do we add them? Well, it was interesting, but for this talk, it's going to be particularly interesting, the effect that this has on the completeness result. But let's finish. Sure. I'm hearing.
Sorry, Carlos?
Yes.
Can you hear me?
I hear, yes, yes.
There is a question in the chat.
Ah, sorry, I didn't see it. Thanks. Okay. Okay, perhaps I was a mistake in the slide. Yes, definitely. Thanks, Helen. This is a small V. There is a mistake here. This should be V of I is a set V. It moves to the point of evaluation of V. Yes, sorry for the mistake. Thank you, Helen. Yes. Okay, so yes. Sorry, I was thinking on my head. I didn't read my slides. Okay, so this should be that if it moves the point of evaluation to the point who is in the extension of the V. So this would definitely be a V, not a W. Okay. So just to get the feeling of these things, notice, for example, that you can write now some things like, for example, I and P. I and P says, I'm in the point I and also P holds. So this is a nominal, so this is Carlos Eduardo Areces, and something happens of Carlos, he's Argentinian. Then it was going to be true that at Carlos, Argentinian is happening, okay? So this implication always works, but for example, this conjunction is not the same as the at, because the other implication does not work. At IP just said that at the I point, P is the case. It's not saying that the current point is P. So this implication doesn't give me that the current point is I and P. Okay, the current point might not be anything at all, might be a J or no nominal, but the only thing I'm saying is that if I would move to the point I, there I'm going to find P, okay? Okay, but let's advance a little bit more. We investigated these languages quite a lot. They add expressive power to the language because, for example, again, just an example, not because it's really interesting, just to show what you can do. If you say I and diamond I, you say, and if a point satisfies this, then the point has to be I, and in addition has to be able to access I, creating a reflexive loop. No? So W will be related with W, so it can force a reflexive loop in one point, something that classical basic modal logic will not be able to do, because we'll be closed under bisimulation, and in bisimulation I can only unloop the loop, okay? So it gives you additional expressive power at the same price. You can prove that satisfiability is still p-space complete. But in addition to that, the important thing is that now we have the material to do Henkin witnesses. And this is what I want to show now, okay? So let's move a little bit. What it is a hybrid now normal logic? Well, it's going to be a modal logic. And in addition, you need to axiomatize your hybrid machinery, okay? But this is not very difficult to do at all, The only thing that you have to realize is that each of these new add operators, they are normal modalities. So they satisfy the K axiom and the necessity rule. So no problem there. They will not behave in any particularly funny way. They are normal operators. And in addition, because you want them to do some kind of equality reasoning, then you have to impose that they define a congruence. For example, at I, if you move to the I point, for sure you will find I there. So reflexivity in this way always going to hold. Also symmetry. If at the I point you find the J nominal, then at the J nominal you will find the I nominal, and so on. Okay, but I'm not interested so much on presenting the whole axiomatization but okay. So you need some additional axioms beside K. They are not even so many, and they are very natural, in my opinion. And then again, then you have a minimal hybrid, normal hybrid logic that we will call H, in the same way that we got K before, okay? So you have now a set of formulas which we define as a minimal normal hybrid logic, and you can define a maximal consistent set there, and you can do Lindenbaum's lemma, Lindenbaum construction, without problem. It works exactly the same, and actually you can even build the standard canonical model, because these actions are very, very natural. You can do the completeness theorem, and you get the same result that for K, doing exactly the same as we did before. Okay, so you can build the maximal consistent, the maximal consistent set and the canonical model exactly as before, and that's it, without any witnessing. So the ideas that we were using before works exactly the same. But the point now is that we can do a little bit better, exactly now incorporating the idea of witnessing. And I'm going to show you how you do that, okay? Patrick introduced the notion of a maximal consistent set being named, and then he called them pasted or pasted. I don't know exactly why. I would call them witnessed, because look at what you can do now. No, so name it's fine. You can say that the maximal consistent set is named if it actually contain a nominal. Okay, and look that in general your consistent set might be named, but some are not, because you could insist that you have exactly the negation of all the nominals. No, not this nominal and not that one and not that one, and then those that negates all nominals, they will not be named. So you ask at least to include one nominal. We will see why they will be nice to have. So some maximal consistent sets are named, and some are pasted, or witnessed, in my opinion. When they are witnessed, if this happens, if you have a diamond inside, and even you can say, well, I have them, my maximal consistent set actually says from inside that in the I point there is a diamond. And remember, and now we remember that this diamond is an existential quantification. Then I can actually witness with a nominal. I can say, well, this says I has a successor where phi holds. Well, let's call that successor J, and let's say then that I have a successor that is J, witnessing with a constant, as Henkin was doing for quantifiers, the name of that successor, and say that at J, phi is the case. So you see how here the unnamed object that was mentioned here, now saying exists a successor, now I witness them with the G constant, okay? So I'm witnessing here quantifiers, okay? And so here I said, well, a maximal consistent set is witnessed if all its diamonds are witnessed, okay? And the point is that now you can do the Lindenbaum construction, but in the stronger way, to get actually that your maximal consistent set, the one that you wanted to get. Remember that we started in the canonical in the previous complexity, or in the previous completeness proof. We wanted first to prove that every consistent set was blown to a maximal consistent set. Now you can get a maximal consistent set that it is named and witnessed and passed it, okay? And again, the idea of Lindenbaums will work as before. The idea is that, well, first, you put it by force a new name from a set of new nominals, and that will preserve consistency. If the nominal is new, it's not mentioned in sigma, then you can prove that you can add it to the set, and that will preserve consistency. And then you extend it. You enumerate all the formulas. If it is if the next formula is inconsistent, then you just don't add it. If it is consistent, then you add it. And if it is consistent and it is of this diamond, then you can witness with a new nominal. And then again, the set that you obtain, you can prove that it is consistent. Okay. So and here, and then you take the limit of that construction. And this is doing exactly what Henkin was doing in his proof of completeness for first order logic. For every existential quantifier, you wanted to add a constant. Now we do it like this because the language let us write that in the language now. Okay? Okay, so you can do it, but what it is for, why it is needed, or why it is interesting, and now I almost finished with the construction. Okay, so we have every consistent set can be extended to a maximal consistent set as before, but now in the hybrid case, I can also make it named and witnessed. That's the difference, okay? Well, and now there is a very subtle change on how we go. Before in the previous construction, we take all the maximal consistent set and we put them in our model, all of them. Now we do different, okay? We do the following. Take one set. Remember that we wanted that it was enough to build one model for each maximal consistent set. This is a bit what we're going to do now. Take one maximal consistent set, blow it to a maximal consistent set, and then we will see that this single maximal consistent set, only one of them, has inside a description of the whole model that we need to create. With only one set, we build the full model. And this is what we call the gossip lemma. Because what happened? Remember that now we have the at operator, and that these sets are maximal consistent sets, okay? So if the set is maximal, and because you have the at operator will include in the set what's going on in every other named set, no? Because if you have any other maximal consistent set that it is named J, then now you have to say at J, such thing happens, okay? So the idea is that the idea of the gossip is that once you know the name of something, you can start telling everything that is happening of that guy, okay? Once you know that I'm Carlos Areces, then you can say, well, Carlos Areces this, and Carlos Areces that, and Carlos Areces what, okay? This is the expressive power that the at operator gives you. Inside one single set, it gives you the ability of describing from the single set the whole model, okay? And then there is some nice properties. You take one single set, for example, and for any nominal that it is in the set, if you take what the set is saying about what's going on in I, so you take all the formulas 5, such that this set is saying, well, at I, this happens and that happened, that set itself is a maximal consistent set, okay? So really you can build all the maximal consistent set that you need from just one. You extract them from inside. So this is also the beauty of infinite sets. Now look that inside this infinite set sigma, which is your single maximal consistent set, from them you extract all the maximal consistent set that you need in the construction of your canonical model. Okay, so this is what you do now. In the hybrid case, the canonical model. Now, perhaps first we should, for example, we should perhaps consider whether we want to call it canonical model or not, because look that it is not one single canonical model. Actually, a better name for this would be a canonical construction of a particular model. It's a uniform construction of a particular model. It is like this. You give me one maximal consistent set, and from that set, I build one model, and that model will satisfy sigma. But we build one different model for each maximal consistent set. Just from one, I can extract from it a full model. The only interesting point is that WC is then built in this way. You just build the elements that you need by the gossip that you get inside sigma. The relation RC and VC are defined as in the previous case. And that then you can prove again a truth lemma that's saying that everything that it is in every set, every formula that appears in one of these sets will be satisfied at that point. But this model that we're building here is definitely not the canonical model that we saw before. For example, it's easy to see, for example, that this is now countable because it has only one element for each nominal that might appear. Now, before the domain was uncountable, now it's much smaller model, it's only countable. And it is named, okay? So, and it is, and well, okay, so you get a different, up to here, you get then a different way of building these models. As I said, it's not a one single canonical model, it will be a set of canonical models. But now, and this is the last slide that I have to say about this, and that's I'm going to slow, and then as I was promising, I'm going to talk 5 minutes more about an application of this. For this kind of models, you prove truth lemma, existence lemma as before, but you can do a little bit more, which is the following. I'm going to show the whole thing. Now, remember that before I told you that you didn't have a guarantee that the canonical model that you constructed in the previous construction will fall in your intended class. So you can build it, you have completeness with respect to that model, but that model could fall outside your class. For particular delta, actually, you can prove that you don't have a chance to put it into your class. So there are incompleteness logics, okay? Well, the result that Patrick and Jerry started proving, then with the thesis of Balder, it got more complete, more detailed, is the following. If you extend your logic with just what we call, or what they call pure formulas, and even you can add rules which are a bit more general, but I didn't want to put them here. But what I'm saying is that if your actions are pure means that they don't use other propositional symbols but nominals, and perhaps top and bottom. So they don't use P, Q, R, just nominals. Then you are sure that your canonical model always fall in your intended class. Okay, so because of the witnessing work that you did, that will be enough to always put your canonical model inside the intended class. Okay, and that follows from these two facts that I listed here. It's very easy to show, to do, but this gives us a fairly simple general completeness result, much simpler than what I think Sarkis 4 pure formulas, and also these existential rules, which are a bit more general. The idea is that this kind of axiomatization is robust in completeness in terms of extensions, as far as you put just pure formulas, okay? And pure formulas are quite expressive. You can do reflexivity, transitivity, a lot of properties can be written by just using pure formulas and existential rules, okay? So, and I think that if you go then into how these work, because I'm running a bit because I just realized that I'm taking more than 1 hour, okay? So sorry for that. So, but this different construction will give us this stronger completeness proof, and well, the nice or the beauty that I was saying is that this is the idea that already Henkin was using, but that nominals and satisfiability led Patrick and Jerry and Seligman and Balder, and then some of my work later do also for this modal logic in this way. Let me just go very quickly. Sorry, any question here? And then I finish. I promised to talk about some new results. These are not new results. I wanted to show you a little bit about something that we did recently. I'm going to continue on the same theme, but on a new logic, on a new language, which is a bit much more complicated. And now the technical part is finished, so you can take a breath and rest a bit. Now what continues, just if you believe it, me up to here, I can show you something which is more relaxed and I think quite interesting. So now I switch for a while. I want to show you a new language that we have been investigating recently, which is XPath. XPath is a query language for XML, so for databases, for semi-structured databases, and it comes from applications. No, XML exists in internet, so it's a way of representing document, and also they invented this query language which is called XPath. They means the internet. Invented the query language which is XPath, which is a query language for accessing this document, for navigating and querying, extracting information from these query languages. I want to show you a little bit about how you can look at them. So XML can be seen as a data tree. So it's a hierarchy of points, and then in each point usually you have either a label. This is a bit the way they think in semi-structured databases, or a data, where data can be numbers and strings and IDs, no? So, but the main difference with a relational database is that you have a tree. You don't have a table, okay? You have a tree. And XML is somehow a way of specifying trees. Then XPath is a language that lets you navigate this tree and query properties of these trees. For example, you want to say, for example, with XPath, something like, go to an ancestor, then check that A is the case there, then go to the child of that ancestor, C should be there, then move to a sibling, go to a descendant, and check B, okay? And this you will write in something like that in a formula, or well, you write these things in HTML or in XML itself, but for logicians, this, look, go to an ancestor, check A. This is basically PDL, as Mario was talking about PDL in one talk before. This is PDL navigation on a tree. No, so you go to an ancestor, then check A, and I'm going to show you that this happens in our tree here. You can go an ancestor and check A up to here. This is the A that you have to check. Then you want to go down and check C there. This is this part. This is not an implication. This is also navigation. Move to the right. I move to a sibling. Then go down and there I check B. So XPath lets you do this kind of regular path navigation using even inverses and sibling relations, moving from X to Y. Okay, so this is just very, very similar to PDL. The only new thing that are these data tests that now let you compare the values that you have at the end of two of these paths. Okay, look that, for example, in this formula here, I'm saying that I have this path, the blue one that I was mentioning, and I have also this green that it is described by just going down and check C, down and C, and then that these two should have the same value, the same data. So this is, so you can think of it as PDL, but PDL that can handle two paths at the same time, together with the ability to make comparisons by equality or disequality on the data of those paths. Okay. Okay. The logic then is quite rich. It has transitivity, and it has inverse, and it has sibling relation, and it has these comparisons. Okay, I'm going to skip this to advance a bit more faster. You can add the hybrid operators to XPath. Why? Well, because it's interesting, so you can write interesting things there. Also, I'm going to skip this slide, but I'm going to show you just the last, this is my last slide because I took already too much time. There was a previous paper in 2017 by Raúl Ferrari. So some of you know Raúl, and Santiago Figueira from the people from Buenos Aires, on an axiomatization for XPath for data trees, and they were doing the canonical construction. And if you see this proof, it's really, really difficult. Okay, so you can see there that they get the canonical model, but then they have to work a lot to really get into the canonical model into your class of models. The work that they do here is really tough and difficult. And then with Raúl, we thought, well, why don't we use actually the Henkin proof? We first have to hybridize XPath, and then in this paper that is recently submitted, we have a previous paper, but this is more in detail. If anybody wants to read it, I can give it. It's also in archive. We show that if you do a Henkin construction, the way that I show it today, the complexity goes much, much simpler. You don't have to argue that your canonical model goes into your class or massage it into, or transform it into a model that goes into the intended class. It just goes there because nominals and satisfiability tell it so, tell it to that it has to go into the intended class. So, well, that's all I wanted to present today. Sorry, I took, I don't know, like 20 more minutes that I intended.
Thank you very much, Carlos, for this really nice talk. So now we have some time for comments, questions, and interactions. I would, as usual, would like to ask you to manifestate first on the chat, just to avoid a lot of people talking at the same time.
Thanks, Valeria, for the clapping, for the virtual clapping. Yes.
Valeria?
Sorry, it always takes me a while to find the button to unmute myself. Sorry about that. Hi, Carlos. Great talk. Really very nice to see the simplifications that you managed to bring to this completeness proof. And I know you said at the beginning that you did not want to talk about constructive hybrid logics or constructive modal logics, but I'm afraid I can't stop myself from asking.
No, sure. I said I didn't say that I didn't want it to. I said that I was not going to in my talk, but I'm happy to talk about. Actually, I'm recently working on intuitionistic hybrid logic and reading your work, so I'm really happy. Yeah.
Yeah, no, so I'm very happy too, because I think that I kind of see now, I mean, as you're saying, because you simplified the proof of completeness, I actually kind of understand better what's happening. And I was wondering whether, you know, whether that will kind of really, if we kind of do it the constructive way, I think the completeness proofs that I have with Torben are of the Henkin style, and I'm not actually sure, but because, you know, it's Torben stuff.
Exactly. Yes, I think that Torben was the one who also included the ideas of hybrid logic inside the intuitionistic proof. Yes, so that's why I think that's working also in the intuitionistic setup, not a problem. Of course, you have to take care, as always, and also the intuitionistic modal logic is more complex because you have to deal with the two accessibility relations, no, to the accessibility together with the increase of information relation. But exactly now, I don't know if Marianela is around there. Marianela is a student of mine who's now, well, you know Marianela, of course.
I do.
Yeah, and she's working exactly on a bit using the ideas of hybrid logic and labeling, and the work on loops, on nested calculus, on hybrid modal logics. And I think that we will continue exploring exactly this path. I mean, how hybrid logic also works on the intuitionistic setup and give rise of a nice model theory also there. Yes.
How lovely. Thank you. That's what I wanted to ask, is whether you thought it, you know, it at least looked like a possibility. And
I think that the more exciting, well, for sure, I think that Torben did most of the work on the well, to Torben and you know, what I'm saying is that he, coming from hybrid logic, probably was the one identifying the use of nominals on the completeness proof. What I'm really interested on seeing also the complexity part, because I never really worked myself on intuitionistic modal logic, and discovering now that there are quite a lot of work to do on complexity-wise.
Yep.
And in particular, I would like to see what the effect of adding of nominals and add does to complexity in the intuitionistic case. Okay, because we have this result that says you take K, you add nominals and add, complexity doesn't change. What happens if you take a hybrid K? No, sorry, intuitionistic K or intuitionistic KT or whatever, and you add nominals? What happened with complexity there? And for what I know, this has not been investigated at all. So I think this, yeah.
No, great. Very nice. I mean, I think it puts things between, you know, it should work because the intuitionistic first order is behind us, holding.
Yeah, exactly. Yeah.
Excellent. Thank you very much. It's lovely.
Any other question? Just a curiosity, in hybrid expert, do you keep the same complexity as hybrid PDL?
Can you repeat? I missed the first part.
In hybrid expert, do you keep the same complexity as in hybrid PDL?
We still don't know the complexity of the whole case. So we know that if you don't have there are not many complexity results for the hybrid XPath with data. So I tell you what we know. If you don't have transitivity, if you don't have if you don't have the reflexive transitive closure, so the logic only with down, and it's still p-space. So hybrid, comparison, just down, even in the multimodal case, that's still p-space. Okay, so in a way, the idea is that you take hybrid logic, you add the data comparison, and you're still in p-space. So you don't, data comparison, in addition to the hybrid logic, doesn't add complexity. But we know, on the other hand, that because of Moshe Vardi's result and and Ulrike Sattler result, there's a very nice paper that shows that even if you go to the mu calculus and you add the hybrid complexity, the hybrid machinery there, then again complexity does not leave X time, okay? Even in the mu calculus. So like the hybrid machinery on top of the mu calculus, they don't add complexity. But we don't know what happens if you go mu calculus, hybrid, test, okay? If there is no jump there when you add this. So we have like 2 of the square, but now we are still working what happens if you put everything together. We don't know. So we don't know if, and you never know. No, these things might explode when you, so everything is fine on 1. If you pick 2, everything is fine if you pick another 2. But if you pick the 3 of things can explode. So we don't know yet complexity for the whole thing. No.
Thank you very much. So do you have any other question or comment?
Yes.
Hi, Sheila. Hi.
Well, I have a simple question. In the usual Henkin completeness proof, you have 2 steps. You first add witnesses, and then you go to a maximal consistent theory. And you sort of mix them up.
I think, yes, you're right. I think that the idea, probably you can do it like first witnessing everything and then just picking the maximal consistent set from there. Okay, I don't know. I think that it's nice to do also the witnessing like on demand. They go very nicely inside the Lindenbaum's proof, because the moment that you want to extend your set, you can at that point decide, well, and in addition, I have to witness this, because then in a way, somehow you only witness the ones that you're using at each point. Mm-hmm. But I think that probably you could like make sure that everything will be witnessed first, and then pick from there maximal set, if you make sure that then you pick enough so that actually you get all the witnesses that you want. I think that this construction just makes sure that you get exactly all the witness that you need, and nothing more than that is added to the language. But yeah, I see your point. But I think that probably you can do it both ways. I don't know. Mm-hmm. If you do it separately, you still want to consider, you make sure that in your maximum, you will still have to prove that in your maximal consistent set, you get all the witnesses that you needed, not that you really wanted. Probably it's not difficult to prove, but you will have to prove it. And here it's more in a constructive way. You are sure that everything is witnessed, because otherwise you will find the point in the Lindenbaum's limit that where you didn't do it. No, in the same way that you argue that it has to be maximal. Okay.
Thank you.
Any other question or comment? So
also a simple question.
Petrúcio?
Is this construction disturbed by the other operators that you can put in the hybrid language or not?
The other operator, which one? The down arrow, you mean, or what? I didn't understand which other operators.
It's a kind of general question. Is this construction robust to the other operators? That's the question.
For sure, you can do the one looked at in a way. Many times we see of hybridization as something that you can do to almost any logic. If a logic is not hybrid, you can always think what happens if you hybridize it. No, and where hybridizing means throw inside the nominals, whatever nominals they need to be, and sometimes you have to decide exactly which kind of nominals you have to use and how the satisfiability operator has to work for that particular logic. If you pick a weird logic, sometimes you have to think, well, if you have a temporal logic that has intervals, then you have to wonder whether your nominals are the point or the intervals or both, okay? So it's not obvious all the time, no? But what I think is that somehow I'm putting the question in the other way around. You can take any logic with any operators, then if you think about how to hybridize it, then you can try to see, well, now can I do a Henkin proof? And probably you will be able to. If you pick the correct witness, the correct object for witness, the correct type for your quantifiers, then the moment that you want to witness your quantifiers, you will have there the nominals that will work as witness, okay? So for sure, you can do this. For example, you take K and you add the pass operator, no problem. You take the universal modality, no problem. You take, we even, I mean, and if you go into more expressive logic, like dynamic logics or Dan Arrow, whatever, also, you will be able to do this kind of witnessing. So yeah, so this is the most I dare to assure what you are saying. I mean, most of the operators, I don't think that there is going to be any problem. You need to have the proper kind of nominals to act as witnesses for your quantifiers. No? Yeah.
Okay, thank you.
One interesting, perhaps last thing I can say, sometimes it's interesting. Also, we saw it in the case for the XPath proof that I was presenting at the very end, that we thought that because of this data comparison and because we were at the beginning not understanding enough in which way the data comparison was working and so on, we thought that we needed something a bit more strange, or we did, and it turned out that just adding the standard nominals for K, for like the simplest thing, the thing that we knew how it worked, already that kind of witnessing will build the whole thing, even for data comparison. So data comparison will not need anything special. So if you see the paper, it's a very neat extension of the paper of Patrick and Balder to a much bigger logic. Yeah.
Any other question or comment? So thank you very much again, Carlos. It was really, really nice.
Thank you for the invitation, and I'm going to definitely continue watching these things. I mean, I watch them with popcorn whenever, so really nice to sit and have 1 hour or 2 hours of these nice talks. Very good work.